Well, so our next speaker, Serhii Koval, with the talk group classification of Kolmogorov backward equations with power diffusivity. Please, you are welcome.
Okay, so first of all, thank you very much. Thanks very much to the organizers for inviting and for giving the opportunity to make a presentation. Well, this is common joint work with Professor Roman Popovich regarding group classification of Kolmogorov backward equations with power diffusivity. Well, we consider the following. The main objects of the study are the following kind of two classes of differential equations. These are 1 plus ultra parabolic, 1 plus 2-dimensional Kolmogorov backward equations with power diffusivity. In the first one, we have kind of shifted power diffusivity, but in the second, this diffusivity gauge to the value alpha equals 0. We denote by theta the tuple of arbitrary elements. Arbitrary elements here are just two real numbers, alpha and beta. And like according just to the general theory of classes of differential equation, we consider the set of arbitrary elements, which is the solution set of the auxiliary constraints on these arbitrary elements, which is, well, simply for the notation introduction, this is just simply the set of these tuples. And here the same. Both these classes belong to and can be embedded in the big class of linear 1 plus 2-dimensional second order ultraparabolic equations of such form, with this big tuple of arbitrary elements parameterizing each of the equation. And actually, well, the relations between the classes are the following. We can embed f prime to f, and in its way f to f bar, which is this embedding arises from embedding of the sets of arbitrary elements via the following injections. Well, beta maps to 0 beta, and alpha beta maps to this tuple of this big class. And actually, this embeddings gives us the corresponding embedding of the equivalence groupoids of these classes. And actually, well, we use the information, the known already information about the structure of equivalence groupoid of this big class in order to compute the equivalence groupoids of these small classes, whose our main problem is to make the complete group classification of these two classes. Okay. Theorem which we proved that the class f bar of these equations is normalized, and its usual equivalence pseudogroup consists of the transformations with components with these components on the transformational part, and this for the arbitrary parameters. T depends only on ty, x depends on txy, y again depends on ty, and u is affine on u, and then we also obtain the corresponding transformation for the arbitrary variables, well, parameters. Okay, and the normalization property played like a crucial role for us to compute the groupoids of that smaller classes. And actually, we straightforwardly using direct method can describe the groupoid of this class f prime. Okay, first of all, theorem, point transformation of such form where we change, where we kind of shift x by c1, y plus c1, 2, and alpha plus c1. This is kind of Galilean transformation. With c1 an arbitrary constant, they constitute a one-parameter subgroup of equivalence transformation of the class f. The wide family of admissible transformations of this form of the class f from the action groupoid of its equivalence group maps this class to the class F prime, which can be interpreted as a subclass of F under the embedding which I showed on the first slide. The point transformation J, this one, is a discrete equivalence transformation of the class F prime. And the class F prime is semi-normalized in the usual sense with respect to the discrete equivalence subgroup generated by this transformation J, which in other words means that the equivalence groupoid G of G sim of F prime is just the Frobenius product of the action groupoid of the subgroup and the fundamental equivalence groupoid GF of the class F prime. So we also know the explicit form of the groupoid of the class F prime. And as a corollary, we have that the only essential equivalence transformation within the class F prime is just this transformation because of the semi-normalization property. So different equation F prime beta F prime beta tilde are similar with respect to point transformation if and only if the sum of betas is 5. And the equation from the class F are similar with respect to point transformation if and only if beta tilde equals beta or beta plus beta tilde equals 5. And the equivalence groupoid GF of the class F is generated by admissible transformations of S alpha beta, which I showed, which is this family of admissible transformation, and the elements from the groupoid GF prime under the embedding of the groupoid under the embedding of the groupoids. Well, or more specifically, for each admissible transformation of this type, we have phi is such composition for some specific transformation phi bar with which is kind of an element of the groupoid of the class F prime. Okay. We also compute the equivalence groups of both the classes using the direct and algebraic method. The equivalence group of this class consists of the point transformations of this form, with epsilon is plus minus 1, and this constants just arbitrary real constants with C3 is not equal to 0. And actually, the transformations with epsilon equals 1 and C1 equals 0, this one, they constitute a normal subgroup of the equivalence group, which is under the canonical projection of the space of this 6-dimensional space parameterized with independent dependent variables and arbitrary parameters to just the space of the independent and dependent variables. We have that this provides us with an isomorphism of the kernel equivalence group of this class. And in fact, the quotient by this normal subgroup is isomorphic to the group to the Lie group R cross Z2, and this subgroup can be naturally identified with the subgroup G tilde F prime, which is generated by this transformation. So under the canonical projection, these are just the canonical choice of the generators of this group, of this quotient. Okay. The equivalence algebra, well, we can straightforwardly compute the equivalence algebra from knowing the equivalence transformations. The equivalence algebra of the class F is spanned by the vector fields dt. This kind of Galilean transformation dy, u, du, and something which is stemming from the kernel. Okay. The usual equivalence group of the class F is generated, well, the corollary is that usual equivalence group of the class F is generated by the one parameter equivalence transformation associated with this basis vector fields of the equivalence algebra of the class F and discrete equivalence transformations of this form. So there are kind of two canonical generators of the discrete equivalence transformation. Okay, this was regarding the class F. As for the class F prime, we also computed the equivalence group using both direct and algebraic methods. And we obtain the following result, that the usual equivalence group consists of the transformations of the following form. These are kind of two, not classes of transformations, just two sets. So we have kind of swap between t and y. So this are okay. The parameters epsilon and epsilon prime are plus minus 1. Epsilon prime, this curvy epsilon prime, is just sign of x, and all the others are arbitrary constants. Well, these transformations of the form 4, they constitute a normal subgroup in the equivalence group of f prime, and which is under the canonical projection. Under this canonical projection is isomorphic to the kernel equivalence group of the class f prime. The quotient of the equivalence group by this kernel is isomorphic to Z2. And it is naturally identified with the identity transformation on this tuple and the transformation J, this discrete equivalence transformation which I mentioned earlier. Okay. The equivalence algebra of this class is spanned by the vector fields dt. Oops. Sorry. Yeah, modulo GF prime equivalence, we can it is suffice to consider the single value of beta between each pair beta 1 and beta 2, such that beta 1 plus beta 2 equals 5 because of the discrete equivalence transformation which I mentioned, which maps beta to 5 minus beta. Well, the equivalence algebra GF prime of the class F prime is spanned by the vector fields dt, dy, udu, tx minus y du, x du, and du. And it is isomorphic to the kernel Lie invariance algebra of the class F prime. And actually, as a corollary, we see that the equivalence group of this class F prime is generated by one parameter equivalence transformation from the associated with these basis vector fields of the algebra, and discrete equivalence transformations of the following form. And in fact, the quotient of this group by its identity component, we can show that it is isomorphic to the order 4 dihedral group. And thus, among this kind of we can choose only two canonical generators of the discrete symmetries. Well, according to the canonical presentation of the group D4. Well, and coming to the main result is the group classification. Well, the group classification of the class F prime, firstly, it consists on describing kernel Lie invariance algebra and all possible extensions. As kernel Lie invariance algebra of the equations of the class F prime is this algebra, where pt, py just correspond dt and dy, and I is udu. And actually, any equation admits kind of extension of the kernel Lie invariance algebra. So any equation is invariant with respect to the algebra G-gen with respect to this algebra, where d beta is kind of dilatation, but which depends on beta. And this corresponds to the linear superposition of the solution of the corresponding linear equation. Well, the maximal and beta actually belongs to this set modulo G modulo this equivalence. Complete list, complete list of the inequivalent essential Lie symmetry extensions of the class F prime is exhausted by the following cases. Beta equals 2, so G2 equals G2 gen plus this vector field, which corresponds to conformal transformation, and beta equals 0. This is the maximal extension, which corresponds to, so we have here also conformal transformation and some specific, well, they correspond to the Heisenberg group, to the transformations from the Heisenberg group of rank 2. And as a corollary, we obtain the group classification of the class F. The kernel-Lie invariance algebra of the equation from the class F coincides with that from the class F prime, and any equation is invariant with respect to this algebra, where d alpha beta is this dilatation operator, and that F alpha beta respects the correspond to the linear superposition of the solutions. And modulo the equivalence stemming from the groupoid, from the action of the groupoid, we can assume that again beta is in the set, and the complete list of GF prime in equivalent essential Lie symmetry extensions, sorry, GF in equivalent Lie symmetry extension in the class F is exhausted by the counterparts from the class F prime. So from F00 and F02. And up to the GF equivalence, it consists of the equation F00, F02, F03, and F05. Well, thank you very much for your attention.